Hello! So, in this video we're going to be talking about geometric series, and in particular we're going to be looking at using closed forms of our partial series. So, in some cases, with sort of certain particular series, we have established a set, what's called a closed form of that series. So I'll show you what I mean as we go. I do want to mention that this is one of those things that it's easy to give some examples and make it look easy, but this is actually an entire active area of research. There are, in fact, like entire sort of research groups of mathematicians that study exactly how to find closed examples, closed forms of weird series of numbers. And in fact, there's sort of an entire sort of web, I hesitate to say web page because that really undervalues it, but a web service and system in place for, so that you can sort of put in a series and get some closed form back if it exists. And if people find stuff that is new, that's not on there, it's worthy of publication and can even get you famous depending on the type of numbers you have. So it's sort of a big deal coming up with closed forms. That being said, we're not going to be handling anything nearly that difficult, obviously, in this class. I just want to make it sort of clear that although there will be several cases where we're going to show closed forms for stuff, I don't want to get across the impression that, like, it is always the case that you should get a closed form and then move forward, because in practice that is very rarely the case. And in fact, this is what sort of numerical methods and numeric analysis and stuff deals a lot with this issue, where if you can't come up with a closed form, how do you sort of approximate a closed form? Okay, so with that caveat aside, let's move into geometric series. A lot of the times geometric series are presented by saying, like, okay, here is all the hypotheses, here's the conclusion, here's why it works. I'm not going to do it that way, because, you know, why do it that way? No fun. So instead, I'm going to sort of build the hypotheses so you can see where they are needed. So I'm going to sort of skip the actual statement of the thing. I'm going to say consider. I will write it, just to be clear. Like, I'm not going to leave you in the dark as to what it actually is. So I'm going to write it at the end, but I want you to see sort of how this is done sort of in practice, albeit with a nice example. So consider the series. So n equals some starting point to infinity of a times r to the n. So n is my dummy variable. It's starting somewhere going to infinity. The only thing I know about a and r is that they are real numbers. I know nothing else yet. My goal here is to understand what things I need to know about a and r in order for this series to converge or diverge, or possibly neither. Like, maybe there are certain combinations of values that I can't tell. Okay? So at first I'm just going to write this knowing that at the moment this is just sort of a purely symbolic thing. This is just a collection of letters and with the summation symbol. I can't claim whether this converges or diverges because I don't know anything yet. Now what I can, so the first observation, so first, notice that if a is 0, then no matter what r is, because it's a finite number, which is important, right? It's not infinity because it's a real number. Whatever r is, I'm going to get 0 times that thing to a power, meaning I'm going to get 0, which means that my sum is 0 plus 0 plus 0 plus 0 plus 0. So my whole sum is 0. Okay? So I'm going to write that down, but I'm going to return to it because you may have an objection. So if a is 0, then a times r to the n equals 0 for every n. So this original series, r to the n, for n starting somewhere to infinity, is really just the sum n equals k to infinity of 0, which is 0. Meaning that I don't even care what r is at that point, I already know the sum. For this sort of stupid reason that a is just assassinating all the terms and it doesn't matter. Now for those of you that took calculus or thinking back to the limits and indeterminate forms a little while ago from the last section, you may have an objection here, which is like, hold on a second. Sure, 0 times any finite number is 0, but n's going to infinity, so if r is like 5, I'm going to get 5 to an infinitely large power. That's something going to infinity times 0. That's indeterminate. So this is a good objection, almost. The key thing to keep in mind, and this is sort of a general thing to keep in mind, so I'm taking this opportunity to point it out, is that 0 times anything, so times some, let's say, x, the limit as x goes to infinity of this thing, this is 0. It's not indeterminate, okay? The thing that makes it indeterminate is if we have something where I have something going to 0 times something going to infinity. So if I have something like 1 over x times x, as it's written here, this is indeterminate because I have something going to 0, something going to infinity. That product could be any number of things. I have to do some stuff. Like in this case, I would have to cancel terms out to actually get an answer. But if it actually honestly is 0, then as x gets bigger, this doesn't change. This is always 0. So your limiting process, you're like, if you think about it as taking x bigger and bigger and bigger and bigger, you keep getting the same number back, 0, 0, 0, 0, 0, 0. And so when you ask, where is that heading to? It's just a long string of zeros. It's heading to 0, okay? So there's a huge difference between it being honestly 0 and something going to 0. And it's a really important difference. So if a is 0, then it's not going to 0, it is 0. So even though this could be getting infinitely large, I'm still getting the sum of 0, it is still 0, okay? So if a is 0, then I don't need to know anything about r. I know it converges to 0, but it sort of does so for a stupid reason. It's just the fact that a is killing off the only term that's doing anything according to my index. And so I'm getting some sort of what we would call a trivial sum, right? I'm getting this thing that isn't really adding anything, okay? So now let's assume, so suppose that a isn't 0. Not because 0 is baffling, but because 0 is boring, right? I've shown what happens at 0, so now let's suppose a is not 0. Now I have to do some work. Okay. So this is another one of those sort of really nice standard construction tricks that I'm going to do that sort of directly speaking doesn't have anything to do with this, except for the fact that it works really well sort of in this circumstance, which is why we're using it. So let's start with note, or actually not even note, let me observe. Meaning I want to just sort of point out this thing, observe. So the nth partial sum, meaning the sum up to capital N, this is a times the first thing, so this is r to the k, plus a times r to the k plus 1, plus a times r to the k plus 2, all the way up to, I'm going to add 2 terms at the end here. So this is going to be capital N minus, let's say 1, a times r capital N, okay? So this is just the definition of Sn, nothing special going on here. But then I'm going to take r times Sn. So the sort of standard trick that I'm talking about that is used is taking some multiple of Sn. Here I'm using r because r itself is going to be really kind of cleverly chosen, as we'll see in a second. So r times Sn, well, if I take r times each term, that's just going to bump the power of r up 1, meaning that the first term, ar to the k, is now going to be ar to the k plus 1. So I'm going to leave this blank just to show that I'm going to get a times r to the k plus 1 as the first term here. And then I'm going to get a times r to the k plus 2. So this thing is actually coming from the n minus 2 term, because I'm, again, adding one more r. So I'm going to get a times r to the n minus 1, a times r to the n. But this is coming from the n minus 1 term when I multiply against r. That gets me here. So I'm going to get one more term, a times r to the n plus 1, right? If I take the last term, multiply it by r, I get this thing, okay? Now I'm going to do something, again, that I can only do because these are finite sums, right? They're big, that's why I have the dot, dot, dot. But that dot, dot, dot isn't meaning that I'm doing something infinitely many times. I'm just following the pattern. These are finite number of terms. What I'm going to do is I'm going to take the difference of these. So here I'm going to get this minus nothing because they don't line up. So I'm going to get a times r to the k. But here's where the sort of nice cleverness works is these are the same, they cancel, they cancel, they cancel all the way down. So I'm going to get plus 0, dot, 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 plus 0, plus 0. And here I'm going to get, just to be clear, this is 0 here, 0 minus that, so I'm going to get minus a times r to the n plus 1. Okay? So in particular, I'm going to write this down right below it here. I have Sn minus Rsn, which if I pull the Sn out, I'm going to get 1 minus r, capital Sn. I have the first term surviving, a times rk, and then I have that thing surviving, minus a times r to the capital N plus 1. Okay? Now I'm going to do one more step, but up to this point, I still haven't assumed anything about a or r other than a is not 0. And technically speaking, I didn't actually need to assume a isn't 0 to do this. I just did it because it's boring if it were 0, right? Because even here I could see if a were 0, this would kill off this whole side. So I'd have 0, and then I have Sn times something is 0, and it would be kind of boring. So, what now? Well, the next step I'm going to do is going to impose an issue. So I'm going to write it down here because it's, well, no, I'll write it up here. I'm going to get rid of the example bit up there. Let's see if I can do that nicely. These markers can be really stubborn once they've had time to dry it all. All right, good. So I'm going to write it sort of framed up here because it's going to be the sort of important bit. So I'm going to write this knowing that you should have an objection almost immediately. So Sn equals ar to the k minus ar to the n plus 1 over 1 minus r. So what you should do, after I finish explaining this, is pause the video, because what you should do is take a second and decide what objection you should have, because there should be an immediate sort of just reflex reaction that you should object right now, okay? So pause the video, figure out what it is, and then I'll say, so you can unpause and see if you're right. Welcome back. I'm sure you definitely paused the video and didn't just say, he'll tell me. So the objection you should have is that I'm dividing both sides by 1 minus r, so if I've done that, I have to implicitly assume r not equal to 1, okay? Because if r were equal to 1, then I've divided both sides by 0, and that is all kinds of bad, right? Like, who knows what's going to happen at that point? So I'm going to make this note that r is not 1, with the understanding that I'll come back to that later, okay? So I'm making a note that what I have done sort of has fallen, like a case has fallen away, that I should address later if I can. Right now I'm just going to leave it off to the side. I'll come back to it, okay? And in fact, just to be clear, I can leave it like this because that's 1 minus r. It is usually done that they take the absolute value of r not equal to 1, meaning that it can't be 1 or negative 1. As you can see, there's no reason to worry about that. It could be -1, and it wouldn't be an issue, except that there are other reasons why it can't be -1, but I'm just saying, for the moment, I'm just going to leave it like that. Okay. Again, I don't know anything about R, don't know anything about A. I do know now that R can't be 1, A I'm choosing not 0, so it's not boring. I'm going to rewrite this a little bit just to sort of make it clear what's happening, but all I'm doing is sort of regrouping. I'm not doing any magic here. So in particular, I'm going to have Sn. This is going to be A times, so that's factoring out the A here. I'm going to have R to the K over 1 minus R times, okay, so I factored out the 1 minus R on the bottom. I factored out an A times R to the K. I'm going to factor it out from both. That leaves me a 1 here minus, A got factored out. I'm going to have R to the n plus 1 minus K. Now I'm doing that because I want to draw your attention to the following. This is a form for Sn. This is what we call a closed form. So back here, and I can't remember if I mentioned this, so forgive me if I'm repeating myself. Back here, we had the dot, dot, dot. This is the key that it is not a closed form because I had to put in the dot, dot, dot. There's something there, but it's understood what is there, right? You can understand it by pattern, but there is something there. But I made them all zeros, which means I could get rid of the dot, dot, dot and write something without, right, that ellipsis, without the dot, dot, dot. So this is why it's called a closed form. I can write every single thing explicitly without needing to resort to some sort of pattern understanding, okay? And in particular, once I've divided by 1 minus R, this is a closed form for Sn. That's one of the reasons why I isolated it like this. So I still have a closed form for Sn, but I've written it in sort of an important way because, right, the n here, in fact, let me use a different color to really emphasize this. The n here is the dummy variable. This is the thing that I'm taking a limit of, right? The limit as capital N goes to infinity to understand the convergence. This thing has no capital N in it. This has no capital N in it. The only capital N on this entire side is right here. And this is where it becomes, this is where we can understand what's happening, okay? Because this is just some number. As long as R is not 1 and A is not 0, K is a fixed number, R is a fixed number, 1 minus R is a fixed number, A is a fixed number, right? All these things are fixed. I can replace this thing with some value, some M or something, right? I'm doing this just by sort of explicit example or to really sort of hammer home the idea. I'm not actually going to do computations with an M, but I could write this as something that does not depend on N times 1 doesn't depend on N minus R times some number plus N, right? So some, again, for the sake of hammering it home, some other number, I'll call it M, which is really 1 minus K, plus N, meaning that the only place where capital N is appearing is on the exponent of R. That's it, okay? So as N gets really big, the exponent of that R gets really big. Now I could have one of really 3 possibilities, except not. If R was 1 or -1, which is why it's often done that this is not -1. So here I'm going to suppose that R is not -1, not because I couldn't handle it, but because I want to make that its own case. So if R were -1, it gets sort of a little messy, so I'm going to do that on its own. If R, absolute value of R, so if R in magnitude is less than 1, then this term, right, as n gets really big, the exponent goes to infinity, something less than 1 goes to 0, right? Then the limit as n goes to infinity of Sn equals the limit as n goes to infinity of this a times r to the k over 1 minus r, which is whatever it is, times 1 minus rn plus 1 minus k. This thing, right, if r is less than 1, this thing goes to 0, this thing becomes 1 minus 0, just becomes this thing. A times rk to the 1 minus r. Which you might note, a times r to the k is exactly the first term, right? So this is sort of, in unofficial parlance, is the first term divided by 1 minus r, okay? So that's if r is less than 1. If r in magnitude is greater than 1, strictly greater than 1, then, again, we'll have limit as n goes to infinity of Sn equals, so the interest of everyone's sanity, I'm not going to rewrite all of this, but the limit as n goes to infinity, it's still going to be of the same thing, but now if r is greater than 1, what happens? Well, I'm going to have something that is big, so by way of example, think like 2, to some infinitely large power, so I'm going to get 2 to some ever-growing number, I'm going to get something ginormous here. So I'm going to get some fixed number times 1 minus some infinitely large thing. So this thing, shouldn't say equals, this thing goes to infinity, i.e. diverges. So I guess I should be a little careful in that I don't know that this goes to infinity. This could go to positive infinity, negative infinity, or it might not exist. So I should say that this thing goes to some sort of, let me rewrite that. I will simply say that the limit as n goes to infinity of Sn does not exist. Okay. And the reason why is because I'm going to get 1 minus something infinitely large times a fixed number. If r is some negative thing, I'm going to get some sort of oscillating thing, right? Because every time it's multiplying by a negative, so I'm going to have some negative 1 to the n times the positive, right, the absolute value of r to the n. So I'm going to get something large and oscillating. So it may just not exist because it's getting infinitely large and oscillating. So it doesn't stabilize on top of being large in magnitude. Okay? All right. So the first part then of this, of what we have, so if, so let's say maybe I'll rewrite the first line. Consider, in fact, I'm just changing colors, not words. So if you're taking notes, you can keep your note there. I'm just doing it to emphasize this is the actual theorem statement. So consider n equals k to infinity, a r to the k. So we have shown, right, if a equals 0, then this sum n equals k to infinity of an, not an, sorry, a times r to the n, a times r to the n. I messed this one up too. That should be an n. There we go. So then this thing is 0. Right, again, the sort of dumb possibility. Otherwise, if absolute value of r is less than 1, then this infinite series of a times r to the n equals exactly this thing where that thing went to 0, right? So it was 1 times this because we had minus, and then this thing went to 0. That was this first case. So this is exactly right here, a times r to the k over 1 minus r. So a times r to the k over 1 minus r. And again, this is one of those things that is sort of implicit in what I've written and yet is easy to overlook unless you've had someone like me hammering it into you at every opportunity, which is that when I say it equals, I'm saying two things. One, this thing exists, i.e. it converges, and it converges to this value, right? So this claim is not just that I have an equality, but that is actually, that series actually converges, right? So that's one possibility. So I'm going to do some editing magic to get rid of this part so I can finish off, because I still have the r equals 1 or negative 1, and I still have the other, right, if r is greater than 1 situation. So with that, I'm going to do some magic. Abracadabra. And we're back. All right. So I'm going to write out the last bit of what we have already shown. So we have the if absolute value of r is less than 1, then we know what it is and it converges. And if the absolute value of r is greater than 1, then this infinite series, n equals k to infinity of a times r to the n, diverges. Because the partial sums fail to exist. Okay? All right, so we're not done yet, right? We still have the case where r is 1 or negative 1. And this is a great example of a time, sort of a classic, I should say, conundrum that we could fall into. So I'm going to take a moment to sort of mention that, which is that a common mistake to make for mathematicians of all levels, and trust me, like, I have a PhD, I have done this mistake, even when I had a PhD, it happens a lot, is that when you are trying to do a proof, when you're trying to get an answer, it's very easy to get locked into a solution method. And it's really easy to do that, especially when it works almost everywhere. You really want to like tweak the method until it works everywhere. And so this is a great example where I could look at this and be like, right, like, I have that it wasn't 1, but I didn't really need to worry that it wasn't negative 1. Maybe I could like shift that into one of these examples and try to like make it work or whatever. But the truth is it's far easier to answer these last two questions where it's 1 or negative 1 without doing any of the stuff that we have done, right? The advantage of the technique that we had, which I've now erased, but that got us, to this closed form, was that it worked on sort of all the numbers there are except 2. Right? And there's many infinite number of numbers, so like trying to do it case by case is very hard. But now that I've gotten it down to just 2 numbers, now I can look at them individually. So in particular, consider the case r is actually 1. Okay? Well, what happens? Well, I have 1 to a power. Right? That power could get infinitely large, but just like we talked about before, this isn't indeterminate. If it were something going to 1 to a power that is going to infinity, that would be honestly indeterminate, but this is actually 1 to a power, which is always just 1, right? It's not something going to 1, and that's an important key difference. So in particular, I have then that the sum n going from 1 to infinity of a times r to the n, sorry, not 1, k, is really just equal to the sum n equals k to infinity of a. And in particular, right, we're saying, we already handled the case where a was 0, so we're saying otherwise, meaning a is not 0. So since a is not 0, I have then that the limit of n going to infinity of the a_n's, meaning the thing I am summing, there we go, which is just a, well, the limit of, as n goes to infinity, of something that doesn't depend on a, doesn't depend on n, is just itself. It is a, which is not 0. So the series It's supposed to be an R. There we go. Series diverges by what? Diverges by test for divergence, right? If the limit is not 0, then the series doesn't converge, meaning the series diverges. Similarly, that should already be a tip-off that I'm going to get something very similar, i.e. the same. Similarly, if r equals -1, then I have that the sum n equals k to infinity of a times r to the k is the sum n equals k to infinity of -1 to the n. Yeah, that should have been n, not k there. Did I make that mistake anywhere else? No. So that should be an n. So this is -1 to the n times a. So I wrote it the other way because that's sort of the standard order to write that in, but r is -1, so I'm just replacing it. And again, so since a is not 0, the limit as n goes to infinity of -1 to the n times a is not 0. So series diverges by test for divergence, right? So in the case where it's 1 or -1, series diverges not by any of the techniques we did before, but just by the honest test for divergence. So in fact, since both of these get lumped into the divergence category, I can say if it's less than 1, we're good, and I know what it is. If it's greater than 1, it diverges. But even in fact, if it's equal to 1, it diverges. Okay? Now, obviously, I didn't explicitly mention it, but it should be clear by context that these things, these a times r to the n, these things are called geometric series. So what makes it a geometric series? Well, I have some constant that doesn't change, which is key. This is one of the things that's sort of easy to mentally overlook. So I have some constant that doesn't change. I could in fact factor it out of the entire series, and some textbooks do that. They define the geometric series without this a specifically for that reason. Regardless, I have some a that doesn't depend on n, and then I have some r that doesn't depend on n, just the r bit, and then I have it raised to the power of n, okay? I want to be very clear here, because in mathematics, a lot of the times we give you these sort of general forms of things, and then we gloss over how it's generalized or not, and we're like, oh, but obviously, you know, this thing is, you know, a polynomial, even though it's, you know, all even powers, because, well, there's really some odd powers with 0 coefficient, blah, 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 right? And we sort of gloss over things. So I want to be very clear here that to be a geometric series, you have to honestly have all of these terms. It has to be exactly this form, okay? I can't have, for example, r to the 2n, because that is not a geometric series, although if I rewrote it as r squared to the n, then that would be a geometric series, okay? But it does make a difference, because then my thing to the n is actually r squared in these forms, not r, right? So when you try to get the actual closed answer, it actually makes a difference that you understand it as r squared to the n as opposed to r to the 2n, okay? So you absolutely have to be able to write it, and maybe I'll write this very explicitly, like right here. You have to get it exactly to the form sum n equals k to infinity of constant times constant to the n. For any k you want, but it is explicitly n, and these are explicitly constants that do not depend on n. So for example, if I gave you a series, let's say n equals 1 to infinity of, let's say, 5 times 2 to the minus n. As stated, just explicitly like this is not a geometric series in the sense that this is not r and a, because that negative n is not just n. But as is often the case, you can take this thing and rewrite it as doing, say, 2 to the minus 1 to the n. Because now I have a constant, 5, doesn't depend on n, 2 to the minus 1 doesn't depend on n, to just the nth power. And that tells me that this thing is r, right? So in particular, this thing would then equal, if I were doing out this example, it would be the first term, which is 5 times 2 to the minus 1. So it would be 5 times 2 to the minus 1 over 1 minus, right? Minus r. R is 2 to the minus 1. So this is 5 halves over 1 minus a half, so 1 half. So this would be just 5. Okay? But if I sort of said close enough up here and tried to do it, I'd get that the series diverges because r is too big. But that's not the case, right? So it's important. And the other thing I want to sort of make clear, because this happens sometimes too, is let's say I have another example. Let's say n equals 6, because I'm just going to make up a number. So let's say I have something like 2 times, let's say, n plus 1 to the n. So here I have a constant 2. Here I have a thing, but this thing depends on n. And so this then cannot be a geometric series. And in fact, not only is it not a geometric series, there's no way to sort of finagle it into one, right? It's not an issue of regrouping terms in some clever way. This is fundamentally not a geometric series, okay? So again, I realize I'm beating a dead horse to some extent, but to be very clear, this is one of those times where the form that we require it to be in is very, 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 very strict. It has to be something times something to the n. Those somethings have to be numbers. They have to be constants. They can't depend on n, right? They could depend on something that isn't the iterating variable if you had some other thing lurking in the background, like there's an epsilon from some part of the proof a while ago. Like that would be okay. But it can't depend on the iterating variable in any way. And the exponent has to be just n, not 2n, not negative n, not n over 2, just n, okay? A lot of the times you can, again, make that work, but if the exponent is, say, n factorial, you really can't do anything with that, right? If it's n over 2, you could sort of pull out the 1/2 like we did here with the negative 1, right? But there are plenty of times where, like if it's n squared or sine of n or something, right? There's plenty of times where you just can't fix it and it's just not a geometric series. Okay? All right. So I realized that was maybe a little bit of more in depth than you expected in some cases. Hopefully some of the examples helped elucidate what I was trying to say. But that is it. And just as a 2-second recap mention, I will say that the method, the way I went about getting this information about r being less than 1, r being greater than or equal to 1, a being 0 or not, this is sort of, right, like what happened was I just started with this thing and I started working with it, and then as I did stuff, I came across natural restrictions I needed to do in order to move forward. And this is a very common way of doing mathematics. And in fact, a lot of the times, there are results that start out with a lot of hypotheses, a lot of restrictions, and then somebody finds a more clever way of doing it where they get around one of these restrictions by doing it instead of, doing some closed form this way, they do a closed form another way, and thus they get around that issue and come up with a more clever thing, and then they publish a better version of the same theorem. And in fact, we'll see that as we go forward. We have like the fundamental ratio test versus the ratio test versus Cauchy's ratio test, blah, 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 right? They all represent fundamental steps forward in the thinking of that same idea. Okay? All right, and with that, we are done.